u by dy. This is the acceleration which is there, is it not? So this is the acceleration as body. So what is the acceleration depends on force, is it not? This acceleration, no doubt, but the force what is generated, the force is what? Force is equal to, so if you consider uh, say for example steady flow, all of things is steady flow. Okay, so let us see. Okay. So let us analyze a fluid element. Fluid means can be air also, can be water also. Let us take a fluid element here. Let us take a fluid element which has, say, this is dx. Here one of the things what we have taken here is we have taken this as x. Understand that? This is x. So that is why here we will take this as dx and this as dy. Understood why? Because along x it is moving. Okay, and if I have a shear stress, see this has shear stress here too. And on the other side, let us say there is another shear stress here where there is a change in shear stress. You have change in dou into dou tau by dou y into dy. Correct? And then the flow is only in this direction, shear is happening in this direction. Okay. Whereas on the other side, there is pressure which is acting. From here, say P pressure is acting, and from the top, there is a pressure which is P plus dou P by dou x into dx that is acting. From dou P by dou x, we know as it goes higher, it becomes lesser, right? But still, let us have that. Okay. So force Fx based on these, okay, the force is actually equal to dou tau by dou y into dy into dx into 1 dou tau by dou y. Okay, dou tau by dou y on this side. This is the total force on that, if you see. Okay, so f of x is this minus this into what is the area, what is the total volume which is there. Volume is dy, sorry, it is acting on this one dx into 1, is it not? So the volume here, this is 1 here, dx into 1 minus dou p by dou x. P is pressure. We always use p as a small, right? So let us use p as small. dp by dx into dx into dy into 1 because 1 is here. There the pressure is active. Makes sense? Then we have the weight, is it not? Minus rho g dx dy into 1. This is the weight. Makes sense? So that is the total force Fx, right? In equilibrium, right? Makes sense? Okay. So this would be mu into dou square u by dou y square minus dou p by dou x minus rho g into dy or dx dy into 1. Correct? Makes sense. Okay. So now, if you consider the whole thing, so density or acceleration, mass into acceleration is the force applied. Right. So if I put it together, I'll get a rho into acceleration, mass into acceleration per unit volume we will get. So everything is per unit volume here. If I divide it by, say, for example, here what is it? It is u into rho g. This is acceleration, mass we will take. Okay, mass is given as rho into, okay, dx dy into 1 into acceleration which is equal to u dou u by dou x plus dou v dou u by dou y is equal to mu into dou square u by dou y square minus dou p by dou x minus rho g into dx dy into 1. What is this actually we have done? We have actually done Prandtl's boundary layer equation through first principles. This is actually Prandtl's boundary layer equation using first principles. If you see that, you should remember. This is Prandtl's boundary. We have used first principles alone. We have not assumed like Prandtl has done. Okay. So Navier-Stokes equation. So you need to get an idea of this also. That it could be derived like this also. So that's why this derivation helps. Okay. So you can write u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p by dou x plus mu into dou square u by dou y square minus rho g. Huh? Kinematics. Yes. Here rho is not. Yes, correct. I'm sorry. This is actually Prandtl's boundary layer equation, but we have derived from first principles. Exactly. Down. Huh? That's fine. The reason is because see tau is acting everywhere in see we have not taken a fluid element which is very small, infinitesimal fluid element. If I take an infinitesimal fluid element, then you can take both sides like that. But here we are talking about shear stress means shear force per area. And both sides, this is also going, this is also going. Both sides, which side the shear stress is there? On this side. It is not a fluid element like we have taken in case of strength of materials. Understand this. This whole element is moving up and it's shearing, of course, because force is less over here, force is more over here. Because this part is more near the wall. Makes sense? So if you take here, I'm taking this part. Here, I'm taking this part. It's moving. Bit difficult to imagine, but here it's easy. Now that we have gone through the very basics, that is what is the advantage we have. Things are very open, very clear. Otherwise, these are the places where we get stuck. And once we get stuck, we don't move ahead. Obviously, when you get stuck, you don't move ahead. And then you cannot remove that thing until you go back to the basics again. And then you come out with the mindset that heat transfer is easy, heat transfer is difficult, or strength of material is difficult, machine design is difficult. All these subjects are difficult. But what is the easiest subject? Manufacturing. Why? Because I can recall, I can understand. Now that you understand this, this is easier. Manufacturing, there are a lot of things. Sir, not possible. It is possible. I'm not saying it's not possible, but still, this seems much easier. Students, entropy, I think you have forgotten. Okay, thermodynamics, revise it again. It's basics. Because entropy is the only difficult thing. Everything else is easier. Not very difficult in a sense. So revise then it will come. Thermodynamic relation, Maxwell's equations. Just to say that when you write it. Then of course, shear stresses in beams. I hope you have not forgotten shear stress in beams. Area of machines anyhow you're doing now. I hope you have not forgotten fatigue because SN diagram, that compression is uh, a friend of material when it is in fatigue. Tension as an enemy. So don't take tension, take load, but don't take tensions. So during gate exam, never take tensions. These kind of shots I should do. Take pressure, but not take tensions because you'll break, you'll have fatigue failure. Sure. Yeah. Similar way, should not have any gaps in your understanding because gaps, holes, and all those things will create stress concentrations. So avoid stress concentrations. Do not have gap in understanding. Right? And do not become too bubbly. If you become bubbly, it creates porosity and the casting becomes weak. Don't get too much excited. Right? Done? Right? Next one. Uh, Now here, generally, for a quiescent fluid, for a quiescent fluid, Quiescent, quiescent fluid, dou P infinity by dou X is equal to minus of, correct? Yes. Which law is this? How did I write this? Hydrostatic. Okay. Now, if there is an increase in pressure, what is going to happen? If there is an increase in pressure, okay. So now, uh, now, see, since since V is much less than U, V is much less than U, dou V by dou X is almost equal to dou V by dou Y, which is almost equal to 0. Correct. That is understood. Dou V, I'm telling you. Okay. Also, 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 there are no body forces in the Y direction. In the Y direction, there are no body forces. So what happens? Dou P by dou Y is nearly equal to 0. Correct. So the variation, therefore, the variation of pressure in the normal direction to the surface is 0. To the surface is 0. Okay. Now, now substituting. Say we have forgot the numbers. Where was the last number we used? We did not use any numbers. Okay, leave it. Leave it. Huh? Don't want. We'll leave it. Okay, we'll leave it. Okay. So now here substituting, say, let us have it here. Okay. Uh, I forget numbers. Putting numbers here. So here dou p by dou x is there, is it not? What is dou p by dou x? Dou p by dou x is minus rho infinity g. Okay. Let me put numbers from here. Okay. That would be much better. All these things are not required. So let us put the numbers over here. Let us put this as A. Let me put this as B, and let me put this as C. Only two. Okay. Substituting, substituting C in B. C B. We can write rho, okay, or yeah, U U dou U by dou X plus V dou U by dou Y is equal to mu into a nu, or this one minus rho g is rho infinity into g. Okay, rho infinity into g, rho infinity into g into plus nu dou square, no rho. Yeah, dou p by dou x is rho infinity into g, is it not? Huh? 1 by rho is there? Wait a second. 1 by rho is this rho. That is, I don't, okay. So nu into dou square u by dou y square, correct? Plus multiply again by rho. Okay, let us do one thing. We will multiply here rho. That would be better. Wait a minute. Let me have here mu. That would be better. This is better. Into rho g. Okay, that way we will do. Okay. Where minus? Minus. Previous. Rho and multiply give together. Now here you can take out g and you can write a rho infinity minus rho. Is it not? Here actually we are deriving Grashof number, and that number is enough. Okay, then everything is fine. Rho infinity is much farther, okay, in the quiescent fluid. Quiescent fluid means this is the plate, hot plate. So let us say this is hot plate, and then there is a boundary layer which is formed. So here is rho infinity, T infinity, U is equal to V is equal to 0 away, correct? Beyond the boundary layer. Right? Same X, and this is Y. Makes sense? Simple. ಆಗೋಯ್ತಾ? ಈಗ now we can write this as rho previous. Take your time. ಆಗೋಯ್ತಾ? ಸರಿ. ನೆಕ್ಸ್ಟ್ ಆಗಿಲ್ವಾ? ಆಗೋದು ಆಯ್ತಾ? ಸರಿ. ಈಗ ನೆಕ್ಸ್ಟ್ ಅದೇ ಬರೀತೇನೆ. U into dou u by dou x plus v into dou u by dou y is equal to, I can say this is mu into dou square u by dou y square plus rho infinity minus rho into g. But beta beta is equal to beta is equal to 1 by rho into rho infinity minus rho divided by t minus t infinity. Is it not? Yes or no? This implies that my rho infinity minus rho is actually equal to rho into beta into t minus t infinity. I can see that. Substituting in equation D. Substituting in equation D. We get rho. I will take out rho now. Mu into dou u by dou x plus v dou u by dou y is equal to nu into dou square u by dou y square plus rho beta into g beta, not rho beta, g beta into g beta into oh. Wait a minute, wait a minute. Ah, yeah, row gets cancelled with this row. This row, this row comes down and it cancels with whatever row is there. So rho infinity minus rho is given as rho into beta, and one row is coming down here and it's cutting. So it is t minus t. Very important one, students. T is very important. Now, this is an important one, so I'll put it like this because this equation may be used a number of times. Okay? Very important. Done. Now let us write all the momentum equation one by one, and then we will non-dimensionalize it. Okay. So when we non-dimensionalize, then we get everything properly. Make sense? When we non-dimensionalize this equation, you get Clash of number. Yeah, tell me. Minus is not there. There's no minus. Huh? Yes. Here it is coming. No. Minus rho g. Correct? No? Correct. ಸ್ಲೋ ಆಗಿ ಹೋಗಿ ಏನು ಗಡಿಬಿಡಿ ಇಲ್ಲಿ ನಿಮಗೆ ಅರ್ಥ ಆಗುವಂತಹ ವಿಷಯ ಅದು. ಸೊ ಇಲ್ಲಿ ಗಡಿಬಿಡಿ ಮಾಡಬಾರ್ದು, ಹಾಗಂತ ಮಲಗಬಾರ್ದು ಮಧ್ಯದಲ್ಲಿ. ಸ್ಲೋ ಹೋಗ್ತಾ ಇದೆ ಅಂತ ಹೇಳಿ ಆಯ್ತಾ. ಯಾರು ಮಲಗ್ತಾ ಇಲ್ಲ ನಾನು ಹೇಳಿದ್ದು ಅಂತ ಹೇಳಿದ ವಿಷಯ. ಎವ್ರಿಬಡಿ ಇಸ್ ವೆರಿ ಗುಡ್ ಹಿಯರ್. Okay, don't worry. Okay. So everybody is alert and concentrating. I know that. Okay. I don't know about online students, but offline students is just pulling their legs. Yeah. Mm. So if they talk, then I'll understand that they are there. So what are the governing equation? Governing equations are for Students, there was a power cut. Okay, so that's why this delay. Okay, so you okay with it now, students?
Yes, sir.
So let us go with governing equations. Okay, this is where we stop. Am I audible, students? One second. Am I audible means are you audible to me? That's what is the question. Okay. So you are audible. I'm audible, students.
Yes, sir.
Yes, sir.
So governing equations for uh, yeah, we have uh, natural convection over heated flat vertical plate, or natural convection over heated flat vertical plate. What are the governing equations? Let us see one by one. If you see here, now this is continuity. If you say continuity, continuity goes as dou u by dou x plus dou v by dou y is equal to 0. Let me put it 1. Okay, let us start with 1 here now. Okay. Next one is momentum. Momentum, I can write it as u dou u by dou x plus v dou u by dou y is equal to nu into dou square u by dou y square plus g beta into t minus t infinite. This is equation number 2. Then what are the other equation you need? You need energy. How's energy equation? Energy equation has convective as well as diffusive part, right? So what is a convective part? Convecting what? Convecting temperature. Here it is convecting velocity. Observe here, here it is convecting velocity. But when it comes to energy, it convects temperature or heat. Heat is related to temperature, right? So that will come as u dou t by dou x plus v dou t by dou y. All are steady state conditions is equal to, what is the right side? Can you tell me? 1 by alpha? No. If you take conductivity equation, where was a 1 by alpha? Alpha, correct. Alpha into dou square t by dou x square. Now we are taking that along x there is no heat transfer. The heat transfer is only along y, because actual heat transfer is only along y, because you're keeping at the same constant temperature. The whole thing you are keeping at the same constant temperature. So what is happening? Heat transfer is only along y direction. So we get dou square t by dou y square. Done. This is 3. Assumes heat transfer, assumes heat transfer only in y direction. Heat transfer. Thermal boundary layer is going along the, in the sense, it is going like this. This is the temperature profile. If you have to write, this will be the temperature profile, right? Or if you consider this would be the temperature. So there is self similarity in temperatures. You see that? So here it may be something like this. Agreed. But these are self similar, and the temperature diffusion in the x direction is very minor. The diffusion is actually in the y direction only. It's only in the y direction, not in the x direction, because temperature difference is more on the x direction, much higher in the in the y direction rather than x direction. Fine, done. Now we have to, let us uh, do the, what are the boundary conditions? Boundary condition BCs are, okay, BCs are in English only. g beta into t minus t infinity. Here there's nothing. Why? Its beta has come only by in the because of the force that it is being generated. This beta does not influence the heat transfer. What does it influence? It influences the movement of the material. When it is heated, its density gets reduced. And what is it causing? It causes motion. Correct. So that motion has to be there in which one momentum equation, not in the energy equation. Make sense? Now at y is equal to 0, u of x comma 0 is equal to v of x comma 0 is equal to 0. Okay. And at y tending to infinity, u of x comma infinity tends to 0, and v of x comma infinity also tends to 0. These are the boundary conditions. And also t of x comma 0 is equal to t of the surface, t wall. Now t is changing, I'm sorry, t is changing along the wall. We are changing because t wall does not remain the same all through here. It changes with respect to x. Okay, and t of x comma 0 tends to t infinity. These are the boundary conditions. These are the boundary conditions. Two boundary conditions we are going to use and solve this partial differential equation simultaneously. Okay, so solving this is easier compared to solving uh, your Navier-Stokes equation because uh, pressure is not there. So pressure term, since it is not there, what we do is generally in CFD, first thing what we solve is energy equation. It's easiest to solve. Energy equation without, yeah, energy equation, the whole energy equation is easier to solve. First, only taking diffusion part, only heat conduction equation we solve. Next, we say convection conduction equation. That's how, if you see Malashekara, we have Malashekara inside. We have a book on CFD on Malashekara. You can see that. First, he starts with diffusion equation with all the central differencing, all the things he uses. Once that is done, next convection diffusion. Then going with next part is only without acceleration, only diffusion equation. Next acceleration diffusion equation. After acceleration and diffusion equation is done, then the pressure velocity coupling. Pressure velocity coupling is the most difficult one. Thanks to Suhas, okay, he has done it well. Is it not? You know Suhas, is it not? Don't know Suhas? Suhas Patankar. Suhas Patankar is a person who has found simple. Okay? Simple is pressure velocity coupling formula. How to do it? He had an algorithm for simple. Then there are other things, simpler, simplest. A lot of things additional has come. So all those things we will see later on. Okay, now this much only. ಏ ದೊಡ್ಡದಾಗಿದೆ ಸರ್ ಏನನ್ನ ಹೇಳ್ತಾ ಇದ್ದೀರಾ ಸರಿ ಬರ್ದಾಯ್ತಾ ಫಸ್ಟಿಗೆ ಗೇಟ್ ಮಾಡ್ತೀವಿ ಸರ್ ಮತ್ತೆ ನೋಡೋಣ ಅಲ್ಲ ಸರಿ ಆಯ್ತಾ ಈಗ ಗ್ರಾಶ್ ನಾನ್ ನಾನ್ ಡೈಮೆನ್ಷನಲೈಸಿಂಗ್ equation 2 using x star is equal to x by L. L is the length of the plate. Y star is equal to y by L. U star is equal to u by u infinity. V star is equal to v by v infinity, u infinity. And then T star is equal to T minus T infinity divided by TW minus T infinity. Like this we do. And then we non-dimensionalize the equation. We obtain. I'm not going to say that. We are not going to do that. To convert is u star into dou u star by dou x star. Let's write it along with me, students. Dou u star by dou y star is equal to, you get g beta into t wall minus t infinity into L cube divided by nu square. Nu is kinematic viscosity, nu square. And then you have here T star divided by REL square plus 1 by REL into, it's a complicated derivation, students. That's why I have skipped it. U star by dou y star square. Tell me, tell me, Agastya. This V square is nu square, it's not V square. Which V square? V star is this U infinity. There's no V infinity. U infinity. Now, what is V infinity is important. How do you take V infinity? U infinity is not at infinite, very important. U infinity is the reference number, the reference velocity. Where here, 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 U infinity is the reference reference velocity that is arbitrary, that is arbitrary. It is not something which is, what do you say, which you can say U infinity, you had physical thing there. Here is arbitrary. You say what is the U infinity, you have to stick. Based on that REL you can say, because if you say U infinity here, U infinity is zero. Away from at infinite, what is it? It's zero. So let me change this. Okay, have you written this down? Yes, no? It's okay, not required to change. U infinity. Fine. Done. Now generally reference velocity is taken as the maximum velocity. Velocity, okay, at a section, because it does not remain the same everywhere. It's arbitrary basically. Okay, because you v at the bottom of the plate is less. As you go up top and top, the maximum velocity changes. Makes sense. So it is actually arbitrary. So Reynolds number in fact is arbitrary. Done. Yes, of course. Because more and more other people will start pushing it. Right? Done. Next. Done. Next. Now here, one of the things what happens, this one. Here we'll define Grashof number. Okay. The dimensionless parameter in the parenthesis is called the dimensionless parameter. Dimensionless parameter. Parameter in the square brackets. We have put square brackets. Is it not? Yeah. In the above square bracket. In the above square bracket. Square bracket. Write it along with the students. Bracket is called the Grashof number. Grash Grashof Grashof number. It's called the Grashof number. Grashof. It's called the Grashof number. Generally referred to as GRL. GRL, which is given as GRL. GRL is actually equal to. To remember this today, this is the only thing which a lot of questions will come. TW minus T infinity into LC cube divided by L cube, divided by nu square. Very, very, very important. Questions have been directly asked on this. Very, very, very. The question. Now, if you put it into the equation, if you put this into equation, so applying this in equation. Oh, wait a minute. We have not put the equation number. Is it not 2, 3? Let us put this as 4. Okay, and let this be 5. In equation 4, we obtain we obtain we obtain u and ignoring stars. Nowadays, what is happening in Bollywood, we ignore stars, is it not? We are going with content. So whether it is Shah Rukh Khan or Amir Khan, we ignore them. This can be written as GR GRL by REL square into T star plus 1 by REL into dou square U by dou Y star square. Correct. Now this gives an idea, although it is derived for flat plate, generally it's applicable for a lot of cases. Now when you consider REL here, when you differentiate this, okay. See now if Reynolds number is very high, then it almost becomes like a forced convection. When REL becomes very high, then what happens? This goes to 0. When Reynolds number is very high, it goes to 0. So what is this? This is related to forced convection equation. Does it not make sense? So when REL square is or REL is much greater than GRL, okay, the the effects of forced convection is, or we'll say REL square, okay, is important, becomes dominant. The effects of becomes dominant. So this is very important. REL and GRL, very, very important. Relative importance of that. So this is something which has been asked in a number of applications, number of things. When do you say you consider it as a forced convection or whether you consider it as a free convection? We consider forced convection when GRL is much smaller than REL square. Then we call it a force free convection. Okay? But when REL becomes higher than GRL, then it is forced convection. REL is comparable to GRL, we call it mixed convection. I'll repeat again. REL square is almost equal to GRL, it's called mixed convection. So here one of the important things which comes here is called the Rayleigh number. Okay. So but before that, let us see what is Grashof number. Okay. More importance to it is gone by. Okay. So let me write. Okay. I'll write in a better way. If GRL GRL or GR, I put it just okay. GRL divided by REL square is much greater than 1, then it is natural convection. If GRL divided by sorry wait, yeah, it's natural, REL square is much less than 1, then it is forced convection. And when GRL divided by REL square is almost equal to 1, it is called mixed convection. These questions have appeared, students. Okay, it's a common question which is being asked. So it may come this time in GIT. Very important. We have to always take like that. Is that next one? Another point here is this. Okay. Um, okay. Anyway, okay. There is something called what is Grashof number? Grashof number GR is actually equal to ratio of buoyancy force buoyancy force divided by viscous forces. Okay. It is viscous. So buoyancy force divided by the viscous force is Grashof number. Very important. There is a way to get this. No, that's it. That is only. Okay. So we don't have the other way of doing it. Okay. Now this is done. Now one of the main thing in a natural convection is okay, in natural convection in pure natural or in say when okay so when when GR by RE square, GR by RE square is much greater than 1, much greater than 1, which is natural convection. Nusselt number, Nu. Nusselt number. What is Nusselt number, students? Nusselt number is a non-dimensional heat transfer coefficient. Okay. Nusselt number, Nu, L or average or anything. Nu is a function of GR and Prandtl, is a function of GR and Prandtl. Okay. When GR by RE square is almost equal to 1, then Nusselt number, Nusselt number is a function of RE, GR and PR. Prandtl. Nusselt number is a function of Reynolds number, Grashof number and Prandtl number. All the three. And when GR by RE square is much less than 1, then what happens? Nusselt number is a function of Reynolds number and Prandtl number, which gives forced convection. So all the experiments are based on finding the relationship. That's it. This is natural. This is for mixed convection. That is why you require heat transfer data handbook to know what are the different relations. You need to know Grashof number, you need to know Reynolds number, you have to calculate, and then you have to have a data handbook to say that in which condition which is there. And how do you make the data handbook? By doing experiments. Although they are analytical treatments, but they are very, yeah, it's very complicated. So people generally go with data handbook. And some of those can be done using CFD also, computational fluid dynamics. So that's why people go with CFD. CFD is very much used in designing heat exchangers, any heat related application. CFD is used extensively. So there cannot be any designing without CFD nowadays. And if you want to know CFD, you have to know the basics first. And there is another point here which is there, which is called the done. Next point which is there is called not done. Done. No, please don't write. And if you have some doubt which arises also because of my handwriting, please ask.
This is what they first be doing experiments.
Which one?
These are
No. This is not done by the function which is required. That is got by experiments. We have said a function. It is a function of that. What is the function? Sir, whether it is exponential, whether it is sinusoidal, whether what kind of function you are talking about. For that you have to do experiments. And big experiments, lot of experiments. That is why there is one particular subject called design of experiments. If you do all the experiments, it take a long time. So what are the relevant experiments should I do so that I could establish a theory? So these are all based on operation research. Our programming, our linear programming, it's all based on that. Everything is interconnected, students. Everything is interconnected. You
use Taguchi method.
Taguchi's method is one of the design of experiment methods. A lot of methods are there. Taguchi is one of the method which is very famous in this region. Here in this region, if anybody does, I'm not blaming that. It's good. Okay. In this region, we have a different type of things people do on wear. Okay, different type of composites. Okay, people do on blended oils. Okay, here if you see our region, all the engineering colleges, mechanical engineers, what they do on, what is their experiments on? Maximum is on IC engines, And on IC engines, they go with blended oils. That would be their experiments. Second one would be composites, banana fiber, other fiber, coconut fiber, and all those. Fantastic. I'm not saying no. Okay, but what has happened is it has to be commercialized. People don't think about commercialization, and there's nobody to pick it up. A lot of knowledge is there. Okay. Third thing is our yeah, this design of experiments, operation research. Even here there are good research which has happened, but superb research happens when you put it into practice. People have not done understanding to get involved with the industry. I'm seeing yesterday when I was coming, there was one person saying that I have a problem, sir. I have a problem that I'm doing a brick, you see, flammable bricks, flammable bricks. On that, there's a problem with he has invested so much of money, and now he's not able to uh, get the what do you say moisture content removed. So what should we do, sir? Sir, I'll help out. I'm trying it. Okay, not visited his site, but still I'll go and visit site after in January. I'll go and visit his site, and I will see what I can do. Now, this kind of connect had to be done by the engineering college professors, which is lacking basically. We say ಅದೆಲ್ಲ ಕಾಂಪ್ಲಿಕೇಟೆಡ್ ಉಂಟು ಸರ್ ಅದು ಮಾಡ್ಲಿಕ್ಕೆ ಆಗುದಿಲ್ಲ ಅದು ದೊಡ್ಡ ದೊಡ್ಡದು ಮಿಷಿನ್ಸ್ ಹೇಗೆ ಮಾಡೋದು ದೊಡ್ಡ ಮಿಷಿನ್ ಅಲ್ಲಿ ಸಿಂಪಲ್ ಕಾನ್ಸೆಪ್ಟ್ಸ್ ಇರ್ತದೆ ಆ ಕಾನ್ಸೆಪ್ಟ್ಸ್ ಅನ್ನು ಅಪ್ಲೈ ಮಾಡಿ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡಿದ್ರೆ ಗೊತ್ತಾಗ ಒಂದೇ ಸತಿ ಬರಲ್ಲ ಇಟ್ ವಿಲ್ ನಾಟ್ ಕಮ್ ಇನ್ ಅ ಡೇ ಯು ನೀಡ್ ಟು ಪುಟ್ ಎಫರ್ಟ್ಸ್ that's it. Now here there is another thing called a Rayleigh number. Okay, so this Rayleigh number is given as it is very very important. Okay, a Rayleigh number, Rayleigh number, very important. Rayleigh number. The Rayleigh number is equal to RA. Rayleigh number. Okay. This Rayleigh number is actually equal to Rayleigh number is equal to RAL is given as GRL PR, which is equal to G beta into T wall minus T infinity into L cube divided by nu square into PR, which is actually equal to G beta into TW minus T infinity into L cube divided by nu into alpha. Nu into alpha. Okay, this is very 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 important. Okay, sometimes what we happen is this RAL Rayleigh number with respect to L, okay, is sometimes given as a ratio of some, can be viewed as a ratio of RAL, it can be ratio of buoyancy forces. This comes as match the following students: buoyancy forces divided by thermal diffusivity and momentum diffusivity. Buoyancy forces divided by thermal and momentum diffusivity. Generally, it sometimes Nusselt number is sometimes expressed. Nusselt number are often, not sometimes, often expressed as a function of Rayleigh number. So in your heat transfer data handbook, you can write this. Nu is equal to HL by K can be equal to a function Generally, what happens a function of a Rayleigh number, which is generally can be like this: C into Rayleigh raised to n. This is how generally we can say that one of the things okay, in natural condition for natural condition or natural. So now in all these cases in natural convection, all the points which were mentioned, like constant heat temperature, constant heat flux, okay, these all these conditions, based on this condition, different functions are there, okay, which you can see in your data and handbook. Kodandaraman we had it. Is it? Have you had Kodandaraman? Is a red book. Heat transfer data handbook use ಮಾಡಿದ್ರಾ ಇಲ್ವಾ? ಯಾವುದಂತ ನೆನಪಿಲ್ಲ ಸರ್. ಬ್ಲೂ ಕಲರ್ ಇರ್ಬೋದು. Who was the author? Well, whatever be the case, you use that, is it not? In that, why you have to see, after understanding this, you have to see those relationships. Then you have to. Exactly. Rayleigh number is GRPR. That's it. Natural convection. Generally applied for natural convection, but there might be conditions where the mixed one and they use Rayleigh number. Mixed one. Rayleigh number for the mixed one because both are important there. Rayleigh number also comes into picture. Reynolds number comes into picture. So it depends on how the scientist uses it. That's it. How he uses, we have to use. That's it. Done. Done. Very, very important. Very good. Okay. Then you have different horizontal plates, vertical plates, hot cylinder, cold cylinder, then hot cylinder inclined at an angle, hot cylinder, cold cylinder inclined at an angle, the different flow regimes inside the cylinder probably, different Nusselt number derivations are there, equations are there. Depending on that Nusselt number, you calculate H. Depending on H, you calculate the heat transfer. Fine. So let us do some problems here. So theory of natural convection completes. More than enough. Okay. Sure. Okay, you understand that, but the thing is that you say that's a thermal diffusivity and momentum diffusivity meter square meter per 4 per second square. Momentum diffusivity is kinematic viscosity by no dynamic viscosity by density. Correct. Yeah. So I'm not saying it's like that. See, it's like see this is related to buoyancy force, is it not? Rho. Yes. Yeah. Yes. But what happens? What does it represent? It represents momentum diffusion. How momentum is diffused, and how it's a temperature is diffused. In terms of understanding, in terms of the physics, what happens there? The physics is that there is momentum diffusion, there is thermal diffusion, both happening in natural convection, is it not? So that it is represented. Okay. So let us see some questions here. Okay. Very less questions have come on this, okay. But let us see. I should find at least one question. Yeah, there is one question which is given here. Okay, this has come in 2019 uh, question paper. Okay, 2019 thin vertical plate. Okay, and you see how easy the questions are. Okay, so let us. I hope there is no trouble if I. No, I have problems. Okay, I will give the question and then I leave. Okay, so let us have what do you call that? IIT Kanpur, IITK, the gate. जल्दी आओ जी. No audible here. Okay, I'll put it in your this one, students. WhatsApp. I'll put it. Okay, it is 2019 one mark a thin vertical plate of height L. This has come in 2019 one mark question set to. So I write it here. 2019 one mark set to a thin vertical plate. Okay, thin vertical plate. Somehow it's not responsive now on this particular browser. Okay. So maybe everybody is accessing that probably. No, you can download see that. Okay, chalo, we will do that later on. Okay, so we'll stop it here, students. Other things we will see in the next class.